Okay, so section 8.7, enthalpy. Energy is involved in a lot of chemical reactions, and we've talked about these ideas of exothermic and endothermic. So let's just review what that means. An exothermic reaction is one that gives off or emits energy. Exo is like exit, and all of this description is in terms of the reaction. So where's the energy going? It's leaving the reaction, the system. So that's exothermic. Endothermic is energy coming in. The amount of energy that's either given off or that comes in is related to the amount of stuff that's reacting. And that amount of energy can be quantified with a function called enthalpy. So that's kind of a funky word. And we're just skimming the surface of this topic. It's actually a lot more complicated. So if you go on and study this more, don't, well, actually I am lying to you. So, but I'm going to tell you that I'm lying to you. So we're simplifying it. So enthalpy of reaction has the symbol delta, capital H, RXN. RXN is the chemist's abbreviation for reaction. Delta means change in. So we're talking about the change in energy. I can't really give you a good reason why enthalpy is a capital H instead of an E, but we can think of it as the heat that flows. Heat is energy moving from one thing to another. And so that's why it's always going to be a change in energy. And all of this is going to happen at constant pressure. So the sign of this delta H can be positive or negative. And this, all the sign means is the direction in which the energy is moving. So it's the direction. So energy flowing out of the system is like a withdrawal, and that's negative. So if we think of energy as being like money, and your wallet is like the chemical system. Do you have positive or negative feelings when money comes out of your wallet? Negative, right? Energy leaving the system is negative, has a negative sign. And then, of course, the opposite is true. Energy flowing into the system or money coming into your wallet has a positive sign. That's all that negative sign means, is that the energy is leaving. So we're specifying the direction that the energy is moving. So here's a diagram where we're graphing the energy levels of the reactants and the products. In an exothermic reaction, the reactants start out with higher energy. Some of that energy is released, and the products end up at lower energy. This energy is mostly, forgot the word, mostly potential, that's the word, potential energy. So it's stored in the chemical bonds. In the process of the reaction, when the bonds are broken, energy is released. And the result is that the products have less energy. Because energy is conserved. It doesn't just appear and disappear. It had to come from somewhere, and it has to go somewhere. In an endothermic reaction, the reactants start out at lower energy. Energy comes into the system, a positive energy flow, and the products end up at higher energy. So delta H of reaction is negative for an exothermic reaction. Here's an example. This is methane, which is the main component in natural gas. And when we burn this, it reacts with oxygen, forming carbon dioxide and water. And is burning gas exothermic or endothermic? Exothermic. It gives off heat. That's why we burn the gas, right? To make something hot. So over here, delta H of reaction is a negative number. And this tells us that we are releasing 802.3 kilojoules of energy for every 1 mole of methane that reacts with 2 moles of oxygen. Here's an endothermic reaction. In an endothermic reaction, the energy is coming in, so delta H is positive. Nitrogen reacting with oxygen forms 2 NO. It looks like no, it's nitrogen monoxide. Here delta H is positive, 182.6 kilojoules. That means that that much energy is going into the system. Okay, it's always from the point of view of the system. So 182.6 kilojoules of heat when 1 mole of nitrogen reacts with 1 mole of oxygen. Any questions yet? Now, the amount of heat that is emitted or absorbed is going to depend on the amount of reactant or product. Because if you burn 1 mole of gas or you burn 10 moles of gas, which one's going to give you more energy? 10 moles, right? So the amount of energy that is released is dependent on the amount of reactants that are started with. So usually delta H is specified in combination with a balanced chemical equation. And the magnitude is for the amounts of reactants as written. So the equation could be balanced in a slightly funky way, but if it's balanced, then you just use the numbers that are there. The magnitude tells us how much energy, the sign tells us the direction. So it's for molar amounts in the balanced chemical equation. So here's another combustion example. This is propane. Propane is what is in the LP cylinder. LP stands for liquefied propane. We have propane burning with oxygen, and this is going to release 2,044 kilojoules. That means when 1 mole of propane burns, you're going to get 2,044 kilojoules. When 3 moles of carbon dioxide are formed, 2,044 kilojoules are released. The negative sign just means that it's going out of the system. These ratios can be used to calculate the amount of heat for a given amount of reactant or product. So just like we did mole ratios, where we would say like 1 mole of propane equals 3 moles of carbon dioxide, we can say that 1 mole of propane is equivalent to giving off 2,044 kilojoules of energy. And that can be used as a conversion factor. So if we know how many moles of propane we have, we could predict and calculate how much energy is going to be released. So let's do an example. Ammonia reacts with oxygen according to the following equation. Let's look at delta H here. Is this an exothermic or endothermic reaction? Exothermic. We can tell that because of this negative 906. So here's our balanced chemical equation. Calculate the heat in kilojoules associated with the complete reaction of 155 grams of NH3. So we're going to use that balanced equation to organize our information here. 155 grams of ammonia. So under ammonia, I'm going to write 155 grams. And what question are they asking us? Calculate the heat, right? So over here under delta H, I'm going to write question mark, and they're specifying they want that in kilojoules. Now, what was the path we learned last week? Grams to moles to moles to grams. Good. Anybody have any dreams about that? Not yet? That's okay. Grams to moles to moles to grams. We used that when we were given a mass of a reactant and asked to find a mass of one of the products. And we would go from grams of this to moles of this to moles of the other thing to grams of that other thing. So we're going to start down that path, but we're going to take a little detour. We're going to take our mass of ammonia and convert it to moles. But then this equation is giving us the relationship between 4 moles of ammonia and 906 kilojoules of energy. 4 moles of ammonia is equivalent to giving off, remembering from the last slide, 906, that's the right number, 906 kilojoules of energy. That's a conversion factor. We can convert from moles of ammonia to kilojoules of energy. So in our path, what we're going to do is we're going to start with grams and go to moles, and then we're going to take a little detour, and we're going to go to kilojoules. So grams to moles to kilojoules. It's a little bit shorter. So 155 grams of ammonia. And we're going to convert that to what? Moles of ammonia. Grams to moles. Because the equation tells us in terms of moles, not in terms of mass. And then we're going to convert that to what? Kilojoules. The path. Grams to moles to kilojoules. And that matches up with our units on the top, grams to moles to kilojoules. Then we fill in the units so that they cancel out. We want grams of ammonia to go away, so we're going to divide by grams of ammonia. We want moles of ammonia to go away, so we're going to divide by that. And this is what we learned how to do last week. We get all the units in, that's dimensional analysis, it tells us what to do. Then we go looking for the numbers. So let's use our new one here first. 4 moles of ammonia results in 906 kilojoules of energy. So then over here, in front of kilojoules, we'll put the minus 906. Don't be afraid of the minus sign. It'll be okay. And how many moles of ammonia? 4. Because in each of these terms, what's on the top is equal to what's on the bottom. What do we need for this term in the middle? The relationship between grams and moles has a special name. What's it called? Molar mass. Molar mass. So we take nitrogen is 14.01 and 3 hydrogens, and we're just getting those numbers off the periodic table. 14 is the mass of 1 nitrogen, 1 mole of nitrogen, and 3 moles of hydrogen times its mass, and that comes out to be 17.034 grams of ammonia is equal to 1 mole of ammonia. .034 grams. So that needs to go in front of grams, and that is equal to 1 mole. So now we've got it all set up, we just need to calculate. 155 times 1 if you want, divide by 17.034 times negative 906. Make sure that you don't accidentally press the minus sign, and then divided by 4, and that's going to give us a negative number. I didn't leave much space, did I? I'll write that up here. So my calculator is saying minus 2061.02501, and the unit there would be kilojoules. We're not used to seeing negative numbers, are we? Can you have negative mass? No. Can you have a negative number of pencils? No. We can have negative energy, though, because energy being negative just means it's going in the other direction. The negative or positive just indicates the direction that the energy is flowing. Bless you. How many significant figures should our answer have? 3. Because we started out with 3 here, and the heat of reaction had 3. So can we round this off to 206? No, because 2061 is very different than 206. We need scientific notation. So I'm sorry, this has gotten very messy. So here 2.06 times 10 to the 3rd kilojoules. And there's a negative sign in front of that. And that's okay, because energy can be negative. So there's our answer. Question?
So is that just the energy for the ammonia?
That is the energy that is released when that amount of ammonia reacts. So when 155 grams of ammonia reacts with the corresponding amount of oxygen and produces a certain amount of nitrogen monoxide and water, then that's the amount of energy that's produced. We can calculate it for a given amount of ammonia, or for a given amount of oxygen, or for a given amount of water.
So the 906, that's,
The 906 is for the molar amounts given here. So 4 moles gives us this amount. If we had 8 moles, it would be twice as much. Does that make sense? Any other questions? Let's do another example. What mass of butane in grams is necessary to produce 1.5 times 10 to the third kilojoules of heat? And there's 2 questions here. What mass of carbon dioxide is produced? So let's deal with the first question first. Here's our balanced chemical equation. Do you notice anything odd about that? Is a fraction in it. Is it balanced though? Yeah. It's not the ideal form. We learned that it's best to clear those fractions out by multiplying everything by 2. But here, we're including this enthalpy term, the heat of reaction. This heat of reaction pertains to these particular molar amounts. And so we don't want to mess with that. We're just going to use it the way it is. So we're trying to find the mass of butane. So butane, by process of elimination, you could figure out that it's the C4H10. I don't expect you to know that, but I do expect you to know oxygen, carbon dioxide, and water. So this one over here must be the butane. So that's the question mark, how many grams? And the information given is an amount of heat. So over here under heat of reaction, I'm going to write, what am I writing? 1.5 times 10 to the third kilojoules. Now, is that positive or negative? Is it going out or coming in? It's going out. So then it's negative. Okay, what's sometimes quite confusing about heat is that sometimes we'll use a sign to indicate the direction, and sometimes we use words. So in the sentence, necessary to produce, that indicates that the energy is being given off. When we're just using equations and math, that's when we need the sign because we lose all of our words. So there's the energy. So here, we're starting with kilojoules. And we can convert kilojoules to moles because we know that this amount of kilojoules is formed when 4 moles of butane react. So we can convert from kilojoules to moles. Then it's asking us, though, what mass. And then we can go from moles to grams. So the regular path was grams to moles to moles to grams. And we're just going to, tweak it a little bit. The tweak is that we're jumping in right here. We're going to jump in the middle instead with kilojoules. Oop, didn't mean to do that or that. There we go. So we're starting with the amount of energy minus 1.5 times 10 to the third kilojoules. We want to convert that to moles. Since it's asking us about moles of butane, mass of butane, then we want to convert to moles of butane. We could convert it to moles of anything in that equation. It doesn't have to be the first reactant. It's just a coincidence that they keep asking us about the first reactant. And so kilojoules will go on the bottom. Oh, I'm going to have to erase this because I didn't plan ahead very well. And then next, I want to convert to grams of C4H10 and divide by moles of C4H10. when I look at my units then, kilojoules cancel, moles of butane cancel moles of butane, and I'm left with grams of butane, which is what the question wants me to find. So this moles to kilojoules is just from this balanced equation. 4 moles of butane, just like doing the mole ratios. I put a 4 in front of the moles, and the kilojoules is just the heat of reaction that's given. Go ahead and put the minus sign in there. Minus 2658. What's the relationship between grams and moles for butane? It's the molar mass, right? It's like, well, I remember what to do, I just don't remember the name of it. That's okay. So 4 times the mass of carbon and 10 times the mass of hydrogen. Four times 12.01 plus 10 times 1.008 equals 58.12. That means 58.12 grams of butane is equal to 1 mole. So 58.12 grams is equal to 1 mole. So now we have negative 1.5 times 10 to the third times 4 divided by negative 2658 times 58.12, and we get a positive number. So 131.196 blah 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 grams of butane. How many significant figures should it have? 2, because what we started with had 2. So then I'm going to round this to 1.3 times 10 to the 2 grams of butane. The negatives ended up taking care of themselves. This was a negative and that was a negative, and so the negatives canceled out, and we end up with positive. Understanding the negative positive sign of the heat of reaction is not super important. So if you're doing it and you're coming up with a negative number and it should be positive, you can just get rid of the negative sign because all mass should be positive. Any questions about that part? So that's the first question. And the other question is, what mass of carbon dioxide is produced? So here we can do the same thing. Kilojoules to moles to grams. But now it'll be moles of carbon dioxide and grams of carbon dioxide, because that's what the question is asking us to find. So 1.5, it's a negative 1.5 times 10 to the third grams, no, kilojoules. Ay, ay, ay. I'm going to convert to what? Moles of carbon dioxide, CO2. What am I going to divide by? Kilojoules. I want this unit to go away. And then next, I'm going to go to grams of CO2, and I want to divide by moles of CO2. So the units work out. You will get the correct answer more frequently if you take the time to write out the units and make sure that they're canceling out correctly. So, moles to kilojoules. That we're going to get from the equation, just like we get mole ratios. So CO2, we find it in the equation, it's got a 4 in front of it. So we write 4 in front of it. we find the heat of reaction term minus 2658. So we put that in front of the joules, kilojoules, 2658. And then we need CO2, the molar mass. So we've got 1 carbon and 2 oxygens, and that comes out to 44.01. So 1.5 times 10 to the third, negative 1.5 times 10 to the third, times 4, divided by negative 2658, times 44.01 equals. That should have also 2 sig figs. That comes out to 99 grams of CO2. You can calculate the amount of energy from any reactant or product. From the energy, you can calculate the moles or the mass of any reactant or product. Any questions? Yes?
Just to be clear, the 1.5 times 10 to the third is negative because it says necessary to produce?
Yes. It's producing. It's not absorbing energy, it's producing it. And if we don't put the negative there, we have the negative on this one and we end up with a negative mass. Any other questions? So in the homework, now all of a sudden they start talking about capital Q. Q is heat, just like it was when we did Q equals MC delta T. They're often going to request the absolute value of Q, which means if it's a negative number, make it a positive number. If it's a positive number, leave it a positive number. Because what they're going to do is they're wanting the value, the magnitude, and they're going to use words to convey the sign. They're going to say, calculate the heat absorbed or the heat emitted. And they're going to tell you they just want the absolute value. They want it as a positive number. So just be aware of that when you go to mastering chemistry, because otherwise that can kind of mess you up. So we looked at a lot of combustion reactions just now. We do that reaction a lot in the lab when we use a Bunsen burner. We're burning the natural gas. And here's some neat pictures of various stages of adjustment of a Bunsen burner. If the Bunsen burner has its air valve closed all the way, all choked off, it looks a lot like a big candle. And it's got a yellow flame, it gives off more light, and it also gives off quite a bit of soot, smoke. And so it'll get the bottom of your beaker all black with soot, and that's kind of nasty to get off. If we give it a little more air, then the flame starts to get more blue. So that's a little bit of air, and here is the best amount of air. And we've got that inner blue cone right there. And usually this flame is somewhat noisy, and that's a good sign. If we keep going and opening that and give it too much air, then we get this floating, it looks like the flame is floating. This flame is not going to be very stable, and if you get a breeze, it may blow the burner out, and you obviously don't want that to happen. So if your burner keeps going out, cut back on the air a little bit, and so that it doesn't end up floating like that. So it's just kind of an interesting little thing your book threw in this chapter. So here's chapter 8 in review. It's kind of the big ideas.